Hello, class. So on this video, we'll continue on the example we're working on in the previous video. Right? So we're talking about autonomous differential equations. Just as a summary, we're working with this example. We're trying to see what information can you find from an autonomous differential equation. Right? So the first thing we saw is that we can always find equilibrium solutions. Right? What are equilibrium solutions? Well, given a differential equation dy dx equals f of y, the equilibrium solutions are the constant solutions which correspond to the solutions that make f of y equal to 0. Right? So we went over that. Here we went over that work. In this case, f of y is y minus 2, y plus 2 times y. What makes that equal to 0? Well, that's an algebra problem. We found that to be y equals 2, y equals negative 2, and y equals 0. Now, we mentioned that this already gave us some information about other non-equilibrium solutions, right? So solutions that are not constant, right? And specifically, these equilibrium solutions, which are horizontal lines, serve to partition our xy plane, meaning that solutions that lied in a particular region would have to stay in that region, right? So I drew a couple graphs of that, a couple non-equilibrium solutions for you to see that. For example, y equals f of x. We know it crosses through a point 0, 1. So wherever it goes, it has to stay on the region corresponding to y equals 0 and y equals 2. It can't cross. Right? The same for anything, for example, on the intervals, the blue solution that goes through the point 0, negative 1, it has to stay in the region between y equals negative 2 and y equals 0, etc. So that already tells us some information about our solutions. Depending on where, if we know one point that they go through, we know what region they stay in. Right? That's basically the idea. Now, I mentioned there's even more information we can find. So what I did here is that I plotted, again, this picture of the xy plane just with the equilibrium solutions. And now I'm going to tell you what other information we can get. Okay? Well, it's as simple as this. Notice that this equation is dy dx equals something. Okay? Now, if you go back to calculus 1, if you remember, given a function, its derivative can tell us something very important about that function. In particular, the derivative of a function tells us on what intervals is the function increasing and on what intervals is the function decreasing. Right, so if you remember, if y prime is greater than 0, then y is increasing on whatever interval this is true. If y prime is less than 0, y is decreasing. So we can do something similar here. Usually on some interval, right? Usually this interval I is an interval about the x-axis, right? So for example, you're given something like f of x equals 2x squared plus x, right? You would find its derivative and you would say, okay, on these x intervals, my function is increasing and my function is decreasing. Now, we can do something similar, but in this case, instead of looking or finding intervals about the x-axis, we're going to find intervals about the y-axis, right? Meaning that we're going to be able to tell on each of these subregions, right? We have subregion 1, subregion 2, subregion 3, subregion 4. On each of these subregions, we'll be able to tell whether our function is increasing or decreasing in that region. And that's the other piece of information we're going to have. Now, it's as simple as what you would do in calculus 1. All we need to do is we have the derivative. All we have to test a y value in each of these regions or subintervals, any y value you want. If that y value, when you plug it into this expression, if it's positive, then that means the derivative is positive, meaning that all solutions in that interval or region are increasing. If you test the y value and you get a negative value, that means that all solutions in that region or interval, y interval, are decreasing. As simple as that. Okay? So we have our 3 regions, right? We have actually 4 regions. We have 4 regions. So we have region 1, which corresponds to the interval y. So this is intervals about the y-axis. So negative infinity to negative 2. We have region 2, which corresponds to the interval negative 2 to 0. Region 3, which corresponds to the interval 0 to 2. And region 4, which corresponds to the interval 2 to infinity. And again, these are y-axis intervals. And we're not working with the x variable. We're working with the y variable. Okay. So again, as you would do in calculus 1, simply pick a y value in each of these subintervals and plug it into this expression. Okay. So for example, let's say on the first interval, we pick y equals negative 3. So we pick y equals negative 3, plug it into the expression. So we have negative 3 minus 2 times negative 3 plus 2 times negative 3. Again, let me say that it doesn't matter what this value is. All that matters is whether it's positive or negative. So a shortcut you can do is, okay, negative 3 minus 2, that's negative. Negative 3 plus 2, that's still negative. Negative 3 is negative, right? So we have negative times negative is positive times negative is negative. That means that our derivative is negative on this interval, on the interval negative infinity to negative 2. Okay. Now let's do the same here. Let's pick something between negative 2 and 0. We can pick, for example, y equals negative 1. Do the same thing. Plug it into the expression we have for our derivative. So we have negative 1 minus 2 times negative 1 plus 2 times negative 1. And again, it doesn't matter what the value is, just whether it's positive or negative. So negative 1 minus 2, that's negative. Negative 1 plus 2, that's positive. Negative 1 is negative. So negative times positive is negative times negative is positive. That means that all or let me say it this way, the derivative on the interval y equals negative 2 to y equals 0 is positive, meaning that all solutions on that region have to be increasing. Now let's test the value on the interval 0 to 2. We can test the value y equals 1. So what do we get? Have 1 minus 2 times 1 plus 2 times 1. Again, the only thing that matters is the sign. So 1 minus 2 is negative. 1 plus 2 is positive. 1 is positive. So negative times positive is negative times positive is negative. That means that the derivative is negative on the y interval 0 to negative 2. And in fact, let me also label them here on this picture, so we can have all the information in a single spot. I'm going to write it in green. So our derivative was, let's see, negative on this interval, positive on this interval, negative on this interval. Now we have one more interval to test, so let's go ahead and do that. Okay, so a value in the interval 2 to infinity, let's just choose y equals 3. Plug it in, so 3 minus 2 times 3 plus 2 times 3. And again, all that matters is the sign. 3 minus 2 is positive, 3 plus 2 is positive, 3 is positive, positive times positive times positive is positive. Meaning that that derivative is positive on the y interval 2 to infinity. So let me write that here. And again, since the derivative in terms of applications for our solutions, the derivative tells us whether our functions or solutions are going to be increasing or decreasing. Meaning that now, if I want to plot a solution that goes through the point, let's see, what color should I use? Let's use purple. If I want to plot a solution that goes through the point 0, 1, now, not only do I know that this solution always stays in this region from y equals 0 to y equals 2, I also know that this solution has to be decreasing, meaning that if I draw it, it has to look something like this. It has to be explicitly decreasing. Now, let me remember or recall you something that I wrote in the previous video, that one of the facts about equilibrium solutions is that they serve as horizontal asymptotes. And I said I was going to talk more about this later. So what does it mean that our solutions serve as horizontal asymptotes? For our purposes, that's going to mean that as x becomes very large, or in either direction, either the positive or the negative direction, our solutions have to approach the asymptotes. So let me write that as an important fact here, or as a note. So this would be, I think, note 3, right? Let's see, where's my previous note? Yeah, so note 3. Note 3. So I'm going to repeat what I mentioned in one of the previous videos. One of the points or the facts about equilibrium solutions, meaning that equilibrium solutions act as horizontal asymptotes, meaning that non-equilibrium solutions which we know are solutions of the form y equals f of x, right? They're not constant solutions, approach the asymptotes as x grows large, or let me write it in Calc 1 notation. No, let's just do it regular, actually. Let's not bother with that. As x grows large in the positive or negative direction. It works in both directions. Which means, going back to this graph that I have here, this is why I drew my function here in purple. Let's call it y equals f of x. This is why I drew it like this. I know it has to be decreasing, and because of this note, I also know that as x becomes really large in the positive direction, it also has to be approaching the horizontal asymptote. Right? In this case, since it's decreasing, it has to be approaching the horizontal asymptote y equals 0. Now, as x grows really large in the negative direction, this also has to be the case. The only way I can draw this is like this, because again, our function has to be decreasing as you read it from left to right. Remember, functions or graphs are read from left to right. So if you see this picture that I drew, for negative x values, this function is still decreasing. Not only that, since it's decreasing on the left, so to the left, for x values less than 0, it has to be approaching one of the two horizontal asymptotes, either y equals 2 or y equals 0. The only option is y equals 2. So I know, even though I don't know what this solution is, this is a rough sketch of what the solution looks like. It's going to look something like this. Now let's plot solutions in other regions. Let's use a different color. Let's say I want to plot a solution that goes to the point 0, -1. I know that this solution is increasing on this interval, meaning that as I draw it, I have to draw it strictly increasing. And as x grows large, it has to approach either y equals 0 or y equals -2. Since it's increasing, the only option is that it's approaching y equals 0. Now for x values less than 0, again, the only way to draw a function that's increasing would be something like this. And again, it's increasing because you read the graph from left to right. As you move from left to right and you're drawing this graph, your pencil has to be going higher, not lower. Okay? Again, it has to be approaching one of the horizontal asymptotes, either y equals 0 or y equals -2. The only option is that it's approaching y equals -2, so it looks something like this. Let's call this function y equals g of x. I'm basically going to draw one in each region. Now, let's say I want to draw a solution on the region. Let's see, what other color should I use? Let me use blue again. So a solution that passes through the point 0, 3. Oh, and let me note that, again, based on the fact I gave you in a previous video, these solutions cannot cross the asymptotes, right? That's why I draw them without crossing, just approaching the asymptotes. Okay? If I want to draw a solution here, how does it look like? Well, it has to be increasing, right? So the only way I can draw it is something like this. So in this case, this solution, at least for values of x greater than 0, can't approach the horizontal asymptote y equals 2, right? Because it has to be increasing from here. To the left, however, it will be approaching the horizontal asymptote y equals 2. And again, this is increasing because you read the graph left to right. Finally, one more region to draw a solution in. Let's do it in, I guess, orange or yellow. If I want to plot a solution that goes to the point, let's do 0, -3, on this interval, it has to be decreasing. That means that as x grows in the positive direction, it has to be going down, okay? Going down, sorry. Meaning that for positive x values, this solution can't approach the horizontal asymptote y equals -2. However, for x values less than 0, if we draw an increasing function, it will look like that. So for x values less than 0, it will look something like this. It will be approaching the horizontal asymptote y equals -2. Again, without crossing any of the horizontal asymptotes. Now, this picture that I drew here, as it is right now, this is what we call a phase portrait. So let me write it as definition 2. The picture drawn above is called a phase portrait. And as you can see, again, we don't know what these solutions are. Actually, let me give this other function's names. I forgot to do that. So it's using blue here for the top one. Let's call this one y equals h of x. And then let's call the one in yellow y equals a of x. So this picture is a phase portrait. What do you need to draw in a first portrait? Well, you draw the xy plane, you draw the horizontal, the equilibrium solutions as horizontal asymptotes. You label whether the derivative is positive or negative on each interval. If you remember that is these signs here. And then finally, you don't have to, but you usually also draw one solution in each region so you know how the solutions look like. Okay, so that's what I did with these functions here. And this is what we call a phase portrait. Again, I know nothing about these functions, y equals h of x, y equals f of x, y equals g of x, and y equals a of x, other than that they go through the points 0, 3, 0, 1, 0, -1, and 0, -3. However, using the information I got from the autonomous differential equation, now I know on what regions do these solutions lie and whether they're increasing or decreasing. Finally, the last thing I know is their long run behavior, which I kind of drew, but we can write down. Okay. So what is the long run behavior of these functions? So let's start with y equals h of x. Let's say I ask you, what is the limit as x approaches positive infinity of h of x? What is that equal to? Well, you go to the phase portrait, you know that y equals h of x lies on the region or on the y interval, y equals 2 to infinity. The function has to be increasing, right, without bound, right, because there's no horizontal asymptote above, y equals 2. So you can either look at the picture or use that sort of reasoning and say, okay, this has to be infinity. Similarly, if I ask you what is the limit as x approaches negative infinity of h of x, right? So again, h of x is on the region of the y interval corresponding to 2 to infinity. We know it's decreasing. So as x grows larger in the left direction, it has to be approaching the horizontal asymptote as we drew it here, right? So another way to write that is the limit as x approaches negative infinity of h of x equals positive 2, which again is just a picture that I drew. So 3 very important things to get for phase portraits. Okay. On what region do these solutions lie? Are the solutions increasing or decreasing? And finally, what's the long run behavior of solutions? Right? This here is what we call long run behavior. And again, this is very useful. As I mentioned before, and I've mentioned a couple of times, a lot of the differential equations you actually work with in practice, you won't be able to actually find solutions. Right? You won't be able to. Right? The ones that we work with in class are very specific. So if you cannot find a solution, well, with this process, at least you know how the solutions behave. And a lot of times that tells you a lot about the model that you're trying to or the system that you're trying to model with the differential equation. It might even tell you everything you need to know. Okay, so very important. So I'm going to do one more example in the next video. I'm not going to go through as much discussion. We're just going to do another example of drawing a phase portrait for another autonomous differential equation.